Hi everybody, my name is Aaron, and today I wanted to talk about a project I worked on last year for my undergrad thesis. While I was in college, I did some research on image analysis using artificial intelligence and machine learning, and I always wanted to see how it applied to games, especially the more I learned about models like AlphaStar for StarCraft 2. So I worked on creating a new method for machine learning models, specifically ones usually meant for image analysis, to analyze strategy games and predict the best move at any state. As you can see here, I have it running in a console. Originally, I wanted to make it in Unity and give a cool visual aspect to the project, but this is about as far as I got because at that point I realized I had no idea how to use a machine learning model in Unity, so I decided to leave that problem for future me. But before we can get to all the cool AI stuff, I had to make the actual game. I wanted to make it as generic and simple as possible, to increase the chances that my method works on other games. I based it a little bit on the Civilization game series, just a very dumbed down version. Each game has two players that fight each other. Both players start with a single town that produces a worker every so often. The workers can move around until they find a good spot and then create a barracks. Over 8 turns, the barracks spawns 2 soldiers and then disappears. The soldiers can attack and destroy enemy troops and buildings, and the winner is the last player with pieces on the board. I gave each unit and building a lifespan, so the board doesn't fill up with infinite units, which is what happened early in testing. I also used to have another unit and building, a settlement that spawned settlers which could create towns, in an effort to emphasize keeping your infrastructure safe. But I found that it took too long for each player to be able to attack because they just didn't have soldiers. Also, it just wasn't fun with the extra units. The first element of the AI involves an algorithm called Minimax search, which is commonly used in other games like chess. A very advanced version of it was used for the Deep Blue AI that beat Garry Kasparov in 1997. If you've never seen it before, Minimax search may seem overwhelming, but it's really just a way to tell if one possible future state is better than another. I'll draw out an example here with tic-tac-toe, which is a slightly simpler game than chess. Beginning from an empty board, assuming you have the first move, there are 9 possible states after one action. At this stage, you want to maximize the value of the state because you're the person playing. After the opposing player makes their first move, there are 72 possible states, so I'm only going to draw out 2. At this stage, you attempt to minimize the value of the current state, because that's what you assume the other player will do. So let's say that you have some way to calculate the value of a state, called a utility function, maybe by the number of open lines that you can use, or the number of lines that have 2 x's in them. You get the values of these 2 states as 5 and 10, and because the opposing player will minimize the value to you, the value that you take is 5. You can assume that none of the other states have a value lower than 5. So the value of the preceding state is 5 as well. You can calculate this over all the states after one move, and choose the action that results in the largest value. But it's impossible to even calculate how many possible game states there are in chess, and while my game is nowhere near as well designed, the number of game states is similarly massive. So that means you can't fully explore the game space with Minimax search. This is why we use the utility function to estimate how good a state is, rather than exploring until someone wins. But there are ways to search more efficiently. I use 2. The first and easiest of them is called iterative deepening. This principle is that you fully explore up to a certain depth, starting at 1 or 2, then restart the search and go one step further. You continue this until you run out of a predetermined budget of states that you can explore. You're required to restart the search every time because you can't store those thousands or millions of states in memory, and if you select a move based on information from a depth you haven't finished exploring, it could result in a non-ideal move. The next method is called alpha-beta pruning. I won't go too in depth, but the idea is that you track the highest and lowest possible values for all of your moves. At this minimization step, we find that one of the possible states results in a value of 10. You already know that the second move in the maximization step has a value of 15, so that guarantees that the third move will have a value of 10 or less, because the opponent is trying to minimize your value. Since you already know that the second move is better anyway, You can skip searching any states that result from the third move, saving some of your budget. The other big part of the AI is the machine learning. Because I'm using image analysis models, I went with a convolutional neural network to analyze the game states. Through my interactions with people outside the AI space, I know that machine learning and the math behind models is pretty intimidating and usually doesn't make much sense. I blame a lot of that on researchers trying to make their work sound cooler than it is and reach the page count on their papers, but that's a bigger problem than we have time for today. In reality, some of the math is fairly easy to understand, including the building block for these models, the convolution. For a convolution, you start out with an image, which I've represented in blue, and a kernel, which I've represented in orange. The image is just a square, or 2D array of numbers, either in black and white or multiple channels for RGB. The one I have here would be a 5x5 black and white image. The kernel is very different, because it's a 2D array of the weights of the model. These values get modified throughout training based on how well the model is performing. The kernel can really be any size, but 3x3 is the most common. To perform a convolution, you take the kernel and sort of slide it along the image and multiply it with every 3x3 group of values in the image. Multiplying the kernel with part of the image is just taking the product of each corresponding value and summing them all together. Each time you do this, you get an element of the output, which I put here in green. That's really all there is to it. In these models, most of the time you have multiple kernels for each convolution, but this just repeats the same step, again with the new kernel, and gives you another channel for the output. For this project, I used a version of a model called ResNet. ResNet's biggest contribution was in the residual connection. Basically, you would take the input, perform two convolutions on it, then add the raw input back to the result. Combining multiple of these blocks together provided a pretty massive boost in performance for classification models because of the additional context it provides the model. So we have the model, but since it's made to process images, how can I make it process information from my game? The naive way would be to give it a single channel where every unit is assigned a value, all the empty land is 1, and all the non-traversable tiles are 0. But this would unfairly bias the model towards certain units because they have a higher assigned value. Instead, I gave the model multi-channel input. The first channel is the land mass of the level, 0s for non-traversable tiles and 1 for land. The next 4 are ternary channels, or channels that contain 3 types of numbers for each unit type, -1 for enemy units, 1 for friendly, and 0 for none. Finally, the model gets a channel showing the age of each unit, so it knows when each unit will disappear. This has worked fairly well for me, but there's always room to improve, so please comment if you have an idea for how to change it. Or even better, go to the GitHub link in the description, modify the code to try it out yourself, and come back telling me how your model performs better than mine. Now that we have the model, we can train it. There's a technique called Q-learning that is commonly used for strategy games and evaluating state-action combinations. You start with a Q table that represents the quality of each game state and possible action. For this, I have a hypothetical game with 6 states and 8 possible actions. The table is initialized arbitrarily, so I just added zeros. Let's say that you start at state 1 and need to choose an action. Because every value is 0, you can choose randomly and pick action 5, which takes you to state 3. You then observe a reward at state 3, represented as R of S3. Then, given some value as a learning rate, you set the Q value of state 1 and action 5 as 1 minus the learn rate times the existing Q value, plus the learn rate times the reward you observed. Assuming that the reward at state 3 is 5, and the learn rate is 0.5, the new Q value is 2.5. By exploring the game space enough times, you can fill out the entire table with accurate values and be able to pick the ideal action at any state. But similarly to Minimax search, we can't model the entire game space for my strategy game, so we look to deep Q learning. Deep Q learning operates in a similar way, but instead of storing an entire Q table, you use a machine learning model to calculate the Q values. At the start of every game, we create a copy of the model, called a target model. Then, at each training iteration, we calculate the target model's output for the next state, add the reward observed from that next state, and use that as the target value for the training model. As a note, the next state is after the opposing player makes their responding move. We then get the training model's output given the current state and calculate the loss between it and the target value. The loss is just the difference between the two values squared. By calculating the target model's Q value using the next state and the training models using the current state, I hope to encourage it to predict the opponent's move better and better throughout training. When calculating the loss, the model doesn't perform any minimax search, but it does when selecting a move. This was also done to encourage it to predict the opponent's moves better. Essentially, instead of using a utility function, the model just calculates the value of a state when the search reaches the maximum depth. When training the model, I had it play 100 games against two types of opponents. For the first 25 games, it played against a hard-coded model using Minimax search. Then for the next 75, it alternated between playing against the hard-coded opponent and a slightly modified version of itself. I also tried a version of the model that only played against itself, though it performed slightly worse. Each game it selected from 5 different levels, vertically flipped them 50% of the time, and added a random set of units and buildings for both sides 80% of the time. This was done to increase the model's exposure to unique situations in the game. 2 other levels were kept out of the training set to be used just for evaluation. To evaluate my model, I compared it to a few simpler alternatives or baselines. The lowest quality baselines were the random and the greedy bot. The random bot picked any valid move with a random number generator. The greedy bot picked any move that resulted in creating a barracks or attacking an enemy. If none of those existed, it picked a random move. I then used a Minimax based baseline with a state budget of 5,000. I also used a few different versions of my model to test what affected it. I had a self-play version of the model that wasn't trained against any hard-coded opponent, then 3 models trained with state budgets of 1,000, 2,500, and 5,000. In order to accurately compare these 7 different players, I had them play against 4 constant opponents, Minimax algorithms with state budgets of 1,000, 2,500, 5,000, and 10,000. I can then compare all the strategies based on the number of wins they have against these constant opponents. I had them play 2 times on each of the 5 maps used in training and the 2 unseen maps, the second time vertically flipped. This amounts to 40 games total on the seen maps and 16 on the unseen ones. As you can see on the screen, the models that I trained generally did better or equal to the Minimax algorithm. On the maps used in training, my AI won 15% more games with the same budget and 10% more on the unseen maps. Weirdly, on the unseen maps, my model with a much lower state budget of 1,000 outperformed every other strategy. Maybe it just got a little too excited and wanted to mess up my results. Even though this is a small improvement over the hard-coded algorithm, I find it impressive because the model consistently wins more while being given the same information. The utility function used by the Minimax algorithm is the same as the reward function for the model, so it's not like I showed any favoritism. I think it would be interesting to see this technique applied to another turn-based strategy game. It would also be cool to find a way to use this framework to take the state searching out altogether. I tried a few experiments with attempting to get the model to simulate the state search without actually going through the steps, but I didn't have much luck with getting it to perform well. But those are projects for another day, or possibly another person. I have all this code publicly available on my GitHub, though it is fairly messy, and the link is in the description. I've also put links to some topics I talked about in the video if you want to look into them further. If you have any questions about anything in the video, please comment them and I'll do my best to answer. Machine learning is actually what I do for my day job, so I should be able to at least point you in the right direction. I'm considering doing a series on how to get started with image analysis with machine learning, so if you want that, please let me know. But until then, I hope you all have a good day. See you in the next one.